Well, there we are. Hey, everybody. Welcome back. I know. We're not in the solar shed this week, and I apologize for that, but you know, sometimes you just got to do what you got to do, and this week, my fear was that it is cold out there, and I don't want to be in the solar shed. So, here we are back in my original studio. I'm looking real quick to try to find the, there it is, the connection. There we go. Make sure everything is working. Make sure you guys can hear me. Make sure everything looks like it is all functioning the way it's supposed to be. Just want to make sure that microphone is there. Yes, it is. So how's everybody doing this week? Looks like, oh, I see. That's why I did it that way. Ah, okay. Well, then we need to move that screen off of there, don't we? That's why I did it that way. All right, let's just take this one and move it. Yeah, let's just take it. This one needs to move. Oh, I think that will do it right there. I don't know. Let's just make sure. Yeah, I think that does. Okay. So, hope everybody's doing well this week. I've got a wonderful program planned for you today. I want to spend some time on just the very basics of a solar system. I have been getting a lot of different questions about people who are looking to build systems of their own. And I titled this one Solar System Basics Beginner Friendly. And I did that with a real intention of coming in today and drawing on the whiteboard, which I believe, let's see if we can do this. Let's see if I can get this out of studio mode and put it over. So we have the whiteboard here, and we will draw up whatever we want. And I also want to build a design within probably PowerPoint or something along those lines. We'll draw up the design with the wiring. I'll show you the wiring guide and basically how you want to pick the wire size that you want. We'll talk about some of the basic components of a solar system so that those of you that are a little bit nervous about building your first system can start to understand the concept of what I call the 4 basic parts of a solar system. And once you understand these 4 basic parts, then it's just kind of a mix match of putting those together and getting a combination of what you want. So I hope everybody's doing well. I haven't looked at the chats yet. Let's take a look at who we've got out here today. Where is it? There. I hid it. I know it's here somewhere. I got to figure out where I hid the chat. There it is. Okay. So hopefully everyone is doing good. Oh, that's kind of interesting. That does not work the way I thought it would. Yeah, that's really weird. All right, so we're gonna have to fix that before we can really do what we want to do here. I am going to have to, there it goes. All right, now I think we got it. There we go, got the chat. So I want to say hello to all. Make sure that the chat is working and that we can see these comments. Yes, there it is. All right, and then also up here when we're on the whiteboard, those are working. And if we decide to do a computer share screen, which will be this one here, howdy, camera's working there. Everything's working just fine today. So glad to see you all here. I'm interested in a lot of different things, but first we're going to start with had an interesting breakthrough this week. So I don't know about how many of you know this, but I've been just chomping at the bit to install a fence at my yard. And the idea behind it is I had all these solar panels kind of laying all over the yard, just kind of hee-haw here, leaning against chain link fences and kind of stuff like that. So I got the fence up this last 2 weeks in spite of all this cold weather. And it was extremely, the first day was extremely hard because I had the Home Depot deliver this giant stack of wood, this giant stack of fence posts, this giant stack of concrete, and then the fun of digging post holes, 29 of them became apparently fun. I ended up buying a auger from Harbor Freight instead of renting one because I figured I got 29 of them to do, and even if I can dig them all in one day, I'm really not sure my arms could handle digging them all in one day. But anyway, all that set aside, I got the fence up. And so I took all the panels that I had along the back fence and I just started laying them up. And I got 16 panels across the back fence, and I thought to myself, I wonder if I put these in 2 sets of 8. And then I have a side that I already had up that you guys have seen the pictures of, and I took that 8, that set of 8, and I had an 8 laying on the ground, then I took that set of 8, and I'll put the ones on the side and the one on the ground is one set, run it through one of the MPPTs on the 6000 XP, and take the new 16 and run it on the other. Check this out. This is just fantastic. So I'm going to do screen share here. I'm going to jump over to, I believe, I don't know which screen it is. This one is, oh, you can see them all. Okay, so I am going to show you, this is my solar assistant today, and I am going to, the bit miner is still running. It is 7:15 at night. We're at 36%. I'll explain the percentages here in a few minutes. Battery state of charge. I have to run the battery down a lot further than I thought because when I hooked this up, I found out that I was going to get a lot more electricity than I expected. Today I did 33.5 kilowatt hours of power, and yesterday I got 31 kilowatt hours of power coming from 10 at a maximum of 19. Keeping in mind, this is February 2nd. Sun is not wonderful yet. Just for reference, my home system, let's see if I can look up my home system here. It is, I don't know if I can get to Solar Edge from my computer. We can try though. Oh, look at that, it does have a lot of things, so maybe I can, let's do monitoring. You guys can still see this, I hope. Yeah, look at that. Let's see if I can get the password to work. Oh, look at that, nice. Okay, hopefully this will work and I can actually show you my home solar system. So this can get about 70 kilowatt hours in a day during a normal summer day or normal day thing. It got 40. So my home 13.5 kilowatt system that's mounted on my roof, professionally installed, got 39 kilowatts. My panels sitting against the back fence. And keep in mind, there's 16 of them sitting against the back fence. There's 16 of them that are 2 that are laying facing, what is that, east. 6 to 8 of them laying east with a trailer with a truck in the way, and the other 8 are laying flat on the ground and in between the house and the shed. So those 16 I don't even count. But if we go look at the statistics here, it's crazy. So we look at the statistics. Now you can't really see it from this view, but if I come over here, you can see here I collected 23.22 kilowatt hours from the 6000 XP. That was from PV1 and PV2. And actually, you know what, to see that, we probably could do that from Solar Assistant. Ah, perfect. So we take the charts here, and you can see this is the PV. And this was me playing with the bit miner to determine how I was gonna run it, whether I needed 2K or 3K. I had to switch it to the high power mode, because let me show you on the bit miner. In low power mode, it runs at about 81 gigahash. Which is about 76% of the normal processing power. But over here in the settings screen, you can change it to normal speed or low power speed or sleeping speed. Now, low power speed runs with about 60% of the power, but gets about 75 to 80% of the processing power. So it's more efficient. So when you have plenty of electricity like I do, I like to run it at the slower speed because I get more bang for my buck per se. But what I found out is this morning when I started, yesterday was a complete disaster because I started with batteries that were at 50, 60%. They quickly filled up, and then I was stuck with batteries that were full half the day. If I go to the state of charge here, you can see here today it only made it to 90%, but that's because I turned it on high usage mode. And you can see here, I started way down at about 24%, and that's because I shut off at about 30% and then let the solar take over at about 25%. So tonight, I think I've got this thing set. Let's go take a look real quick. I hope I got it set to shut off at 20%. So automations, no sun, at 20%. That'll give me an extra 10%, which should make up for that gap in the middle. Now, when summer gets here, I'm gonna have no choice but to switch this to run on high-speed mode because there won't be enough batteries to store, or I could just get more batteries. That's a good idea. Yeah, we could think about that. Maybe I'll take the 15 kilowatt battery out of the RV and put it in the shed and just move something, get a new one for that. That's an interesting idea. Anyway, but the whole point is here that I'm talking about is that this thing produced a whole lot more power than I was expecting. And as you can see here, I hit 3 different blocks today on the Quai. And then I've also hit Digimon. I haven't processed any today, but yesterday I ended up with 4,079 coins there. So I am mining pretty well. I'm getting, fairly lucky. I only hit 1 yesterday with this, which was just a pain in the butt. But the Quai went pretty well tonight, and it's still running. It still has, what kind of percentage? We still have 16% of battery to run down here in order to get us into a position where tomorrow isn't the same thing where I'm having to bump up the efficiency. What I'd like to do is have it run as long as it can into the evening. Now, every other day, you can see here, the 24 volt system is sitting at about 50% charge, 49.2, meaning that after 2 days, that system has another 10 kilowatts or so that I need to transfer over, and I use a charge inverter for that. But I can't do that today because the charge inverter is in the RV, because the 15 kilowatt battery that's there wasn't enough to run the heater with 20-degree weather outside. We don't get bad weather here. So my idea was, well, we'll just turn on the heaters and let the heat keep the pipes from freezing. The problem is that it consumed about 12 kilowatts running the heaters, and it only stored 15, and it didn't collect 15. It only collected about 8 or 9. So it had some issues there. Anyway, blah, 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 blah. Just talk. So what I want to do tonight, though, is basically work with you guys to, didn't even see these. Let's see what we got here. Got a couple of comments from folks, so let's talk about this one first. Is Daryl Watts. He says, on my solar panel set, I did 28.5 kilowatt for the day, and so I'm a 28.5, not bad. I got a little bit more than that, but my guess is your panels are probably more efficiently mounted. Literally, I have 16 panels leaned against the back fence. And then 16 more laying here and there, and then all the other panels are just for the 24 volt system. And I think there's like 4 or 5 of those that are just kind of, 2 against the shed, 2 on top of the coffee trailer, and 1 sitting in the door of the shed and everything. And I'll probably send you guys some videos and stuff. But Daryl, it's that's not a bad output. I mean, that's an output of a typical home. I mean, we saw it. My house was getting 39, and that's got a 13.6 kilowatts of power panels on the roof and a 10K inverter. So, and that's a professionally installed one. This thing out in my shed is nothing more than panels laying against the wall, and all used panels at that. So 28's pretty good too. And then NSB Reefs I got 4.7 kilowatt hours. It's all relative. It depends on what you're doing with it. So I did, and I'm kind of a nut, so I have like so many different systems here that it's kind of crazy to say. So here we have this one. I did 28 with that, and then the shed had another 5.7. So that puts us at, that says 28, but I know that's not right. It's interesting that it would say that though. And then these two are the 24 volt system. So I got another 3.7. Oh, that's because this is a window? Oh, that's kind of interesting that it says that, because if you look over here, oh, this is everything. This is both the 48 volt system and the 24 volt system. Oh, okay, that makes more sense. So that means coming from, if I go over to the second tab here, yeah, we'll see the 24 volt system and these two colored ones here. So the, let's see, we have the coffee trailer in that color there. Let's see if I can scroll this up where you guys can see it correctly. Coffee trailer there, the Lux, that's the 6000 XP. The Test, that is also 24 volts. So these two are 24 volts. So that's 3, 4, 4.5, almost 5 kilowatt hours there. And then these two together is 28, 29 kilowatt hours there. So it's pretty amazing. But it's all relative. So it depends on what you're using it for. If I was the coffee trailer just sitting, you know, running my freezers and stuff, it would only be 2.9. So it all comes down to how much you use and how much you need. I've been kind of blown away by it because I was not expecting 30 kilowatt hours in a day. And to be honest with you, it's not even summer and I still haven't got the other 16 panels in a good spot yet. When I get them in a good spot, that's gonna be crazy. Anyway, so how is everybody doing? 13 panels on my house, rated at like 91%. I didn't go over any projections with you. No, I didn't go over any projected, you know, yeah. So 13 panels, yeah. So that's a much, you've got 13 panels. I got a bajillion sitting out there, leaning against fences and stuff, and yours are producing, you know, what'd you say, 28 kilowatts from 13 panels. So my guess is they're probably a little bigger panels than the ones I have too. Mine are all used 250 watt panels that I paid nothing for. I think the first 12 I paid $15 a piece from a farm that was closing down, and the last, so now I know how many panels I have since I'm using them all. I have 16, 32, 32 minus 12 is 20, 20? No, I can't be right. 32, 20, that's not right. I've got some panels missing. 16, and 16 is 32. Yeah, I've got more panels somewhere. Nice. I wonder where. I'm gonna have to look around a little bit. That means I've got more panels somewhere. And in SB, you have 8 panels surrounded by trees. Yeah, a lot of trees. Trees are not friendly. But you know, I hear all the time comments and people telling me, oh, well, you shouldn't mount your panels vertical. You shouldn't do this. You shouldn't do that. You do what you can do. I mean, that is what it is. If everyone could do anything perfect, then it would be great. Amy, yes, this is specifically for you and for people like you, for those that want to, and I think it's about time I get started on this anyway. But at all times, please, chat is half of the fun of this live stream. So, but this is going to be a real total thing. What I want to do for this show tonight is I want to actually build I was going to sit down and build a diagram of a solar system and then make that something that I gave away for people to sign up for the email list and all that kind of stuff. That is going to happen. I will put a subscription to the email list at the end of this and send it out to anybody who wants it. So keep that in mind. If you do want it, you can have a copy of it. It will be a free gift that I give away on all of my live streams going forward. And most of my videos will push it also. It's a good way for somebody that's new who wants to get into it. So I'm thinking of doing 2 things. One, we'll do some stuff on the whiteboard. Because I couldn't, you know, I can't do anything without a whiteboard, And then the second one is to I want to build the actual diagram within probably PowerPoint or something like that. I might be Draw.io or something like that. I'm probably thinking PowerPoint though, because I like the way that works, but Draw.io is kind of easy too, but it's black and white and I can't really get through what I want there. So, and then I'll build I'll actually go out and look up some of the parts too, and maybe include a parts list with links for you guys for that. And that way I can just put it into a package, and you know, anyone who signs up for that will get that package going forward, but you guys all get to be part of the construction of it. We'll just kind of build it together and everything. It'll be kind of cool. And then I was intending on tonight taking the, getting the email list subscription and have you guys go ahead if you wanted to sign up and while we were during this class, and I would send it to the list when I was done. I got caught in traffic. I set in an hour and 40 minutes of traffic before this show, trying to get home, and took up all my time, which is why I was late starting. I could throw things together and get us here. So without further ado, NSB says, I am torn between adding optimizers or adding another MPPT for shading. Yeah, the only problem I have with optimizers is the cost. You know, they cost almost as much as additional panels, and you know, if you could put in. This was one of the tests that I ran. I don't know what voltage your system is in SB, but I ran a test where I did the solar shed, and I was feeding it into a 48-volt system, and you had to have, you know, had to have 3 in parallel to get the basics to work. 4 worked better to feed the 48-volt system, and obviously the 8 that I'm running here now feeds in even better when you have that. But for shading, the problem is to be honest with you, the 12-volt system worked best, because instead of running them in series, and you're running 24 volts, so you run the same thing as my solar, my coffee trailer, and with so you have to probably run 2 panels, and so my suggestion there is to run those 2 panels, run them 2 panels, and then run those in parallel. And so you've got, what did you say, 8 panels? 8 panels. So hopefully you're running those in 2 in series and 4 parallel. And that way the shading only affects the 2 panels that are in that parallel series. Now you can add more charge controllers also, but you can certainly make it much more efficient, because voltage usually isn't the problem. The problem is that a little bit of light and boom, the voltage is there, but then the shade affects the amount of power that they put out. And then, but if you run them in parallel, then each one of them operates independently. Now, yes, if you put in a charge controller for each parallel string, it would be more efficient. But if you want to do it a lot less, like I'm doing here, I have 2 8s against the fence and they get sun all day. But the other 2 8 sets, one is laying on the grass and one is behind a truck. So during and I should actually show you this, because this would be very useful to you probably. Let me see if I can find that chart. I think it's this screen here. Hopefully you can see this now. Let me see if I can show you the in is, no, not that. PV. So here are all the strings. This string here is, you can see here, this is the string that's laying in the grass. And then the second string that is behind the truck, when the sun comes up over the edge of the house next door and hits it, this shoots way up. But then when the sun goes down behind the house, it blocks both strings of panels, and you can see they both die off. So this is what I would suggest for you, is that you put your panels in 2 in series, and then parallel the 4 of them together. And I can kind of show you that on I need to make sure the whiteboard piece is working anyway. So let me just show you that on the whiteboard. So you basically, and I don't know how you have them hooked up now, but you can hook up 2 in series like this and 4 in parallel. And that way, when put that into your charge controller. And what will happen is shading on this set won't affect this set, and so on and so on. Oh, I'm on the wrong side of this board. See, I should have moved that the other way around. But shading on this set won't affect this set, and so on and so forth. And this will allow each one of them to operate pretty good. Now, the only exception to this is if one set is completely dark and don't have any voltage whatsoever. That's very, very rare though. It's hard to do during daylight hours to get one of these, because you'll notice when the sun comes up in the morning, and if I show you, I can show you on the chart here, when the sun comes up in the morning, the voltage on these immediately, probably best shown over here in Solar Assistant. So go over here to charts, and then if I come down here to voltage, so here's current, here's voltage. And so you can see voltage, soon as the sun even begins to look like it's gonna come up at 642, the voltage shoots way up. Now we don't get any power, and you can see this on the right-hand side here. We don't get any power or any current out of them until 9:30. But the voltage is there the whole time. So even though those panels that you have in this series are shaded, they still have voltage to carry so that they don't interfere with the other panels in that parallel group of series. Hopefully that made sense. Anyway, that's just my suggestion on that, is that would be the easiest way to get as much power out of that as you can, is to series them all. So if you've got them, yeah, and you've got them all in series, which means that even if one of them gets, so running them like that, meaning you have 8 panels, switch this to blue real quick, meaning that if you have 8 panels like this, and you're at a 24, 6, 7, 8, and I'm assuming these are home panels that are panels that are producing, if they're like eco-worthy panels, they're probably producing about 20 volts a piece. If they're regular house panels, they're probably producing 30, 35 volts a piece. So depending on how many voltage they are, at 24 volts though, it won't make any difference. You probably need 2 panels to make it work. And so what you're running is you're doing it like this. And what ends up happening now is that any one of these can interfere with all of them. Whereas here, only 2 of them have problems. And this is what when I originally built the solar shed, this was one of the things that I actually tested very extensively. I ran it in 2P, in 2 series, and let's see, 5 parallel, because at first I had 10 panels. And then I changed it to 3 in series and 4 in parallel when I went to 12 panels. And that was why I went to 12 panels, because I needed them to complete the 3 series and 4 in parallel. And then I tried 4 in parallel and 3 in series. And the one that worked the best, now keep in mind, it's a 48 volt system. So for those of you that are new in all this panel talk, the important thing to remember about solar panels is that if you've got a 12 volt system, I'm going to just do a very simple chart here. If you've got a 12 volt system, that means that in order to provide enough power for this to charge, you need 17 volts or greater in order for this to charge. And that's why you'll find that most 12 volt panels are 18 to 20, 21 volt type. Most like your eco-worthy type panels and stuff like that will be 18 to 21 volts. Now, you can still series them and double that voltage and use them for a 24 volt system. If you look at home panels, so that's going to be your small panels. They're going to be like 18 volts to 23 volts, somewhere in that thing. Most home panels are 30 volts to 40 volts. Now, there are some bigger ones now that are 800 watts, 700 watts that may have up to 50 volts, but most of them range in this thing. So for a 24 volt system, you need to get this voltage plus 5. You need to have 29 volts or greater in order for this to charge efficiently. Now, that said, there are some charge controllers that will upcharge this. In other words, you can put in a 20 volt panel like one of these here, and it will charge your 24 volt system, but they're not near as efficient, and they don't work near as well. If you're using anything like a Victron system or a normal MPPT charge controller, you need the voltage of the battery plus 5. Now, that said, I wrote 12 volts here, and technically 12 volts is 13.2 volts, 24 is 26.4 volts, and 48 is 53.2 volts. So you really need this plus 5 volts to effectively charge correctly. So why I'm saying to do this over here is if these are 30 volt panels and he does it, instead of doing it this way, where he has 30, 60, 90, 180, 210, 240, so he's running at about 240 volts, which is very effective, works, but shading affects every panel, shading affects every other panel. So if he gets a cloud that comes over this one, it affects the performance of all of them. He gets a cloud that comes over this one and this one, now he's got a double whammy and this thing really produces poorly. But if he changes it this way, instead of running at 240 volts, he'll be running at 60 volts, but it'll be at 60 volts and the amperage will be multiplied by 4. So instead of each one of these putting out, let's say that it puts out, 5 amps or 10 amps, let's use 10 amps as an example. Instead of it putting out 10 amps at 240 volts, it'll put out 10 amps at 60, and the amps will add together. So it'll be 10 amps, 20 amps, 30 amps, 40 amps, and it'll be 40 amps going into that charge controller. But this, the shading doesn't affect you anymore. And then on the 53 volt one, you really need it to be about, I would say probably 60 volts or higher. This one, I would really put it at about 30 volts or higher. And this one, you could really safely, much safer to go 20 volts on. But this is the basic rules of doing the panel configuration and why that's important. Q cells, I have Q cell 340 watts, but I'm limited to 14 amps with the inverter. You're limited to 14 amp input. Let's just go look at that. The CERN inverter. Probably a maximum of 14 amps input? That could be. And it only has one MPPT. Wow. That's painful. So yeah, it might be better off if you did something like even a single Victron charge controller. So we could do the math real quick. So 340 Q cells, if I remember correctly, those are standard. Let me just switch this screen here real quick. Let me just find that place real fast. Here it is. Switch over here. So let's just go look up those Q cell panels, 315 watt Q cells. All right. I did say 315, right? 340. That's why I'm having problems. $340. This is the wrong brand, but oh, there they are, right there. Top of the dang list. All right. So these are running at 10 amps. And 40 volts. Okay. So what you need is 10 amps, which would be 10.5 amps. Let's do some math here. Let's just do some quick math here. Let's take 2 of these cells is 81 volts, so that should be pretty easy. So your maximum 81 volts you need to be able to withstand. And that's open circuit. You need short circuit. Doesn't say. We'll put in a buffer for it just to make sure. It looks like 100 volts would be safe though. So that was more than 20%. And then you got 240. Let's just grab a calculator quick. 340 watts times 8 is 27. Divided by 81 volts. It's 33 amps. So you need to be able to output 33 amps. So you can get a Victron, you got like a Victron 35. Let's just go look it up real quick. Amazon, let's do a Victron charge controller 35, let's do a 100 slash, I think there's a 35. I think I have one of these in the RV. And that's if you want to go, you know, with no room to change. This 150/45 amp one right here is $211, and it would do it. There it is. There's a 150/35. That's the one I was thinking about, the 150/35. It's 175. And that one you could put them in parallel, and it would charge any of these systems, even at 80 volts, even a 48 volt system if you ever decided to upgrade. So this one would be a good solution too. So either one of those, and this 150, even it would work. It would allow you to add quite a few more panels too, because you'd have 50 amps. Any of these that has the voltage above 100 here, and the amperage you need is 30. What did we say? 30. I don't remember. 33. So you need 35 amps. So anything there, and you would be perfect, and you'd be golden. You'd be able to run these in parallel or in series, and that would get rid of all your shading issues. And so that's where that would go. All right. I know I spent a lot of time on that. We haven't even got started yet. This is what happens when when you let me run rampant here. Peak Duo. Not sure what that's referring to. NSB. All right, so let's start with, I'm gonna take the whiteboard here, and we're gonna just clean the whiteboard off, and we're gonna start with a basic. I wanna get to some basics for newbies and people that are just getting started, or for those of you who've set them up but really didn't know like that. That's not cleaning very good. Let's try a new one. Oh, that's much better. Okay. So let's start off with, and we've got an idea of what the panels that we just went through for the panels. So let's start off with a very basic system, and I don't want to be very complicated. I want to make this very, very easy. Absolutely, NSB, anytime. Always glad to help. And hopefully that was helpful. So, and one of the big things that newbies always ask me is, when you get involved in this, some of the tools that you're going to need, and I brought a few of them here just to kind of give you an idea. One of the things that you're going to need, and you cannot live without, and don't go super duper cheap on it. Don't go to AliExpress and buy a super cheap one. You're going to end up spending $100 or so on a meter like this here. I don't know if you can see this. Let me just make sure my screen is pointing to the right thing here. So these meters This one I think was about 120. It has the clamp on it for the amperage clamp. And this one here just does voltage, continuity, those kind of things. If you're going to hook up any system whatsoever, and you can only buy one tool, this is the one you're going to want. You will use this practically every single day of your solar life. And you can spend on these. These are Kleins. They're fairly accurate. They're not perfect. They've got really super nice ones that are $300, $400, $500 that are extremely calibrated and all kinds of fancy stuff to be perfect and all that stuff. I found these are just perfectly fine for our purposes of setting up a system. But these allow you to detect voltage. They allow you to check for continuity to make sure things are connected. They allow you to measure resistance to make sure you have good connections. They allow you to do that. There are hundreds and hundreds of tools that you could buy, and probably 90% of them are things you will use once. I got a camera on the end of a stick that goes to a little device that I used a few weeks ago when I was in the solar ship, but I've had it for 3 years. I've used it once. I've got an oscilloscope that can measure the sine wave of AC thing. I use it when I get a new inverter and I'm doing some testing to make sure that it is pure sine wave. There are hundreds and hundreds of dollars, but you don't need them. This you will need. This is something you cannot live without. So if I'm making a suggestion for one thing that you want to buy before you get too far into it, it would be one of these. And these you can find practically anywhere. I bought these from Home Depot. They're available on Amazon. You can find them practically anywhere, but this is something that you can't live without. And it has so many different uses, and I will point them out as we go along. For example, on our panels that we were working on before. So we're going to start off with a very simple 12-volt system. And I want to, 12-volt system is a lithium iron phosphate system. I don't want to get into all the details of the different battery types. There are lead acid batteries. There's new sodium batteries. There's salt batteries. There's AGM batteries. There's all kinds of things. But if you're doing solar and you're buying equipment today and you don't already have existing known quantity batteries, my suggestion is you just stick with lithium iron phosphate, because the life of these batteries is fantastic. I charge, as you saw today, I'm downcharging my batteries all the way down to, 8 or 10, 15, 20% every single night. And they're gonna run them all the way up to 100% during the day and then discharge them down every day. Even at 10,000 cycles or 5,000 cycles, we're talking about 10, 15 years of life doing that every day. And you would think that it's an exaggeration, but the fact is it's not. So the first thing you want to do is the life for battery is what you're looking for. It doesn't look right. The reason you want to do this is it has extended life. It can take the charge and the discharge. For example, if you get lead acid batteries, where this one, you can run it all the way down to 0 and charge it back up. And is it good for it? No, it's probably not good for it. But does it do severe damage to it? No, it doesn't. The fact is, these are going to last so long that chances are by the time you did any damage was even noticed in this battery, you will be gone or bought new batteries, because technology will have changed so much. So these, we're looking at the lifespan of, I would say, probably 10 to 15 years. And what's going to happen is the age of the battery is going to age out more than the battery itself wear out. I've got some of these lithium iron phosphate batteries that have, 300 or 400 cycles on them. And I'm not talking about little cycles where I run it down 10% and charge it back up. I'm talking about fulls on, down to 10%, up to 100, down to 10, up to 100. Every single day I work my batteries, because I know that in 10 or 15 years, let's face it, I'm in my mid-50s. 15 years from now, I'm gonna be 70. And to be honest with you, if I can't afford new batteries between now and then I did something wrong. So focus on a 12-volt LiFePO4 battery. Let's talk about the battery is the basics of your system, okay? So if you have a 12-volt battery, and there's a marker here for this. The 12-volt battery is called 12 volts, but it actually is made up of cells, and all of your batteries are made up of cells. And everything that I talk about from this point forward is going to be based on lithium iron phosphate batteries, and not to be confused with lithium batteries. Lithium battery is what is in your cell phone. It is what is in little devices like microphones, like this microphone has a little lithium battery in it. My cell phone has a lithium iron battery in it. iPad, your computer, those are lithium batteries. Lithium iron phosphate, they add the phosphate into the mixture of the lithium. It provides two things. One, it provides stability to the lithium chemical makeup for charging. It prevents it from charging super fast, and it prevents it from discharging as fast. In other words, a lithium battery, when you plug in a cell phone, as little as that cell phone is, you can push that amount of power. You can push an amount of power that overwhelms the battery, and it takes it. A lithium iron phosphate battery, it has charge limits usually equal to its discharge rate. So if you have a 100 amp hour battery, you can discharge at 100 amps and you can charge at a maximum of 100 amps. But it provides stability to that charge and that discharge. In other words, it doesn't have the tendency to have runaways like you would have with a normal lithium battery. Also, it provides sustainability to it. In other words, instead of like your cell phone battery or these little devices where you notice the batteries seem to die after a couple of years, or your cell phone loses its integrity after a couple of years and won't hold a charge, the lithium iron, the phosphate, allows that battery to live much more cycles. Most of these batteries are between 5,000 and 15,000 cycles. 15,000 cycles is crazy because you're talking about 15,000, and even if you cycled it every single day, you're talking about 25 plus years of life out of these batteries. So that means that if you bought new panels and you bought new batteries, you could literally have a system that could be in existence for the next 25 years. So that is why you want the lithium iron phosphate. It provides the stability, the resistance to the fires and that type of thing that you have. Lithium iron phosphate batteries are very, very stable and very safe. So much more than your lead acid batteries, which have chemicals and fumes and stuff like that. A lot of people even park these batteries under their beds in their RV and stuff like that simply because they are so stable and safe. So that is why we want to go from there. And everything that I say from this point forward is going to be based on a lithium iron phosphate battery. So being the main staple of your system, let's talk about what is a 12-volt battery. First of all, a lithium iron battery is made of cells that are 3.2 volts cells. Now, all of the batteries, 12 volt, 24 volt, 48 volt, are made from these 3.2 volt cells, but it's the number of cells that make the battery's difference. So in a 12 volt battery, there are 4 of these cells hooked up in series. And yes, this series is identical to the solar panel example that we went over earlier. So you hook up 3.2 volts and you got 3, 6, 9, 12, 12.8 volt, and there is your 12 volt battery. In a 24 volt system, the only difference is that instead of 4 cells, 1, 2, 3, 4, 5, 6, 7, 8, you have 8 cells, and thus you end up with 25.6 volts as your normal battery. And then if you do 48 volts, you end up with 16 cells, and you end up with 53.2 volts. And they're all made up of these little cells that you put together. Now, a lot of you have seen the little batteries that go into devices, little lithium batteries that go into the biscuit-sized batteries. Those are lithium batteries also. They're not lithium iron phosphate, but they are lithium batteries. And if you look at the voltage, most of them are 3.2 volts. And with them, you can create little miniature 12-volt batteries. You can create little miniature 24-volt batteries, or you can create little miniature 48-volt batteries. And then when the cells get bigger, you create bigger batteries. And that allows you to create any of the battery sizes, or for the manufacturers to build you any of the battery sizes. Now, if you get into this deeply, you may want to at some point construct your own battery. I built a 48-volt battery out of cells that were 304 amp hours a piece, which gave me a 15 or 16.2 kilowatt hour battery that's in my RV. And it used 16 of these 3.2 volt cells. So that's the first thing we want to talk about with your battery, is that they're always made up of cells. So this has 4 3.2 volt battery cells. Now, that said, there is a charge profile that comes with these. And what do I mean by a charge profile? So in a battery that is made up of 4 cells, 3.2 is the nominal voltage, meaning it's not the max that it's charged up, and it's not the min that's charged up. It's just right in the middle of the Goldilocks version, about where a battery floats. And so what you will see is that they have what I call it a profile. There are 3 important numbers to know. And with a 12-volt battery, I'm gonna write this over here so that I can still be on the screen. Notice it's dropping me off the screen. You need a charge voltage, or what we call a bulk charge. Now, bulk means that there is a big gap in where your battery is and where it needs to get, and it can just send as much power as it has up to the maximum of that battery. So if this was a 12-volt battery, the bulk charge for a standard lithium iron, now you want to look at the manufacturer's suggestions, but most of your lithium iron phosphate batteries that are running off of cells like this. Now, there are some exceptions to this rule, so make sure when you're buying a battery that you look at this and make sure that you're watching for it. If there's been any questions, I have completely missed them, so let me go over there, make sure. Okay, there's none. All right, so the bulk charge rate on these is going to be, now here's where we start talking about cell voltages. So the maximum that you want one of these cells to get is 3.65 volts. The minimum, and what I mean by maximum, this is the maximum voltage you want to charge this cell up to. And so if you take this times 4, let's see if I can get my calculator off my cell phone here. We take this times 4, so we have 3.65 times 4. That means the maximum, and some of these numbers will sound very familiar to you, is 14.6 volts. So when you're charging this battery, the maximum you would want to charge it to, because anything more could cause damage to these cells, is 14.6 volts. Now, that would bring each of these cells up to 3.65. But what most people will do is they will charge it to less than this amount here. For example, I like to charge it to about 14.2 volts. Now, if you take 14.2 volts and divide it by 4, you end up with 3.55 volts per cell. Now, the reason I do that is because there are 4 cells in here. And if you have 4 cells, sometimes they're not all the same voltage, and you're going to want to make sure that if this one is sitting at 3.62 and this one is sitting at 3.56 and so on and so forth, that the total sum of this doesn't allow one of these cells to get out of control. Now, a lot of your nice BMSs, your battery management system, which is probably a term you've heard, BMS, and the battery management system, which is what BMS stands for, will watch these cells and allow you to set certain things. So let's talk about the JK BMS for a few minutes. The JK BMS allows you to set the charger to shut off if it gets over a certain voltage. It also allows you to set a balance mode. And balance mode is when these get out of whack to a certain point to allow you to take voltage from this one and move it to that cell here. But there's configurations that allow you to do this, and basically you go in and say, okay, once the cells get up to start getting close to full, if these are out of whack by more than such and such amount, I want you to start moving this voltage around, and that's why the BMS becomes very important. But let's just stick with the basics here. So the charge bulk voltage we've determined is around 14.2 volts. It can be anywhere between 14 and 14.6, depending upon where you're comfortable. My suggestion is you look at the manual. Most of them will put 14.4, and a lot of people will change it to 14.2. A lot of people will bump it up to 14.6, knowing that they're made out of these cells. Then there's a second one, which is what we call float. Now, float is when the battery gets full. You don't want it to sit there at its maximum capacity all day long while the sun's shining and it just sit there all day long waiting. Is there something, time for me to stick more voltage in there, more voltage in there? So what it is this is what we call it. Usually it falls off to a certain amount. And it's also based on this number here. So a lot of people will use a number here to determine how much that voltage is. And so if we look at this and we say the 3.4 volts per cell, it would bring us to a 13.6 volt float. And this brings us up to 3.4 volts per cell is what is considered a full state when the battery doesn't accept any more charge. And how you get to float is that you run the charge in the bulk mode, and when it stops accepting power, then it'll drop down and sit at float. And that would be that time during the day when your battery has gotten all of its power, but you no longer want it to sit here. So usually you can sit at that what they call absorption level, which is usually the same as your charge level, and you'll sit there for a certain amount of time. If your battery is way out of whack, you'll need time for it to move voltage around, then you may want to leave it there for longer. Most people do this for 20 minutes to an hour a day, and that's more than enough for it to balance the battery out. Then it drops back to float and holds there. And then the next day, when this falls off again, it switches back to charge, and it cycles between these two. And that's why this is what I call the battery profile here. And it's very, very simple because these numbers, as we talked about, are based on the number of cells. So therefore, all you have to do in order to do a 24 volt battery is double all these numbers, because all you're talking about is double the number of cells. So we say 28.4 volts for the charge, and float becomes 27.2 volts. And then we double it again for the 48 volt battery. 28.4 times 2 is 56.8 volts, and 27.2 times 2 is 54.4 volts. Now, There are variations of these. For example, here I use 56.2 on my 48 volt systems. And that allows for a little bit more deviation between the cells here. And if they do get a little out of whack, I don't have the BMS come step in and say, hey, look, you got cell number 8 here and it's higher, it's too high, and I'm gonna shut everything down because it's too high. And so this limits that flexibility. Same thing's true over here. I bumped this down to 54.2. Over here on the my 24 volt system, I actually use the 27.2, and I use the 28.4 here. And over on the 12 volt system, I definitely use these. Sometimes I'll actually use 14.4 here as opposed to 14.2. So it really depends on your system, and look at your battery's manufacturer manual. Most of them will tell you charge at 14.2 plus or minus 0.4 volts or something like that. And that means charge between 13.8 and 14.6. And so you'll get that thing from there. But this is the key to your system here, is understanding the difference between charge and float and that part in the middle, that absorption that just allows the battery to just sit at 14.2 volts and just keep taking in the energy until it's full. And then it goes into float mode. Okay, so that is your battery. Hopefully that's very, very clear to everybody what we're working with. So we're gonna start with a 4-cell battery, which means it's going to be a 12 volt battery that is going to be in our system here. Now, typically in a system, I have 4 main components. I have a battery, which we've already decided in this scenario is going to be a 12 volt system. Usually when people start off with a new system and they're brand new to this, I suggest that you build something small to run an entertainment center, a TV. I used to say TV and VCR, a TV and your cable box, or maybe your router, or a small refrigerator or something. Build a small system that allows you to take something you have off grid that isn't of absolute essentials. The nice thing is, if you build one that works with a refrigerator or something, then when you do have a hurricane or something, you have something to keep your food refrigerated and all of that. For reference, most refrigerators, freezers, deep freezes and stuff run at about 1.2 kilowatt hours a day. So that's kind of for future reference when you get into working all the numbers here. Okay. So let's take this battery and let's hook it up to an inverter. Now, the inverter is the piece that is truly optional in your system. Some people, when they hook up a solar system, they only want battery power to power lights, or maybe a small RV where they have a reading light or a fan, or they have 12 volt appliances or something like that. Most of us want to plug in standard household plugs. I don't have anything to show you what a plug, but you know what I mean. With a normal wall plug that you would plug in 110 volts, or in some European, most overseas non-US countries, non-US countries, I guess that's technically true. Well, that does not work the way I want it to. There we go. So this wall plug is 120 volts here. Yours may be 240 volts, but the inverter takes this battery power and converts it to that wall outlet power. So I'm going to put that inverter right here. And usually it will have a wall plug on it. And I'm just going to draw a standard, I'm going to try to draw a standard wall plug. It'll have a wall plug on it, or it'll have connections to run to a wall plug. Now, most of us want this type of power. And so you can buy now the one thing there's several things in these systems that are not flexible for upgrades. The inverter is usually one of those. When you buy it, it's like buying a battery. When you buy it for a specific voltage and for a specific output of watts. And watts are going to be how much power each device you plug into it uses. For example, your charger for your phone. In the case of this one here, if you look on the label on the side of it, this one here says that it inputs 120 volts and 0.8 amps. So 120 volts at 0.8 amps will tell you, and almost every device will either tell you the wattage that it outputs, or it'll tell you the voltage and the amps. And the trick here is the voltage times amps equals the watts. And so all we have to do to figure out how many watts this thing is going to take on an input is take that 120 volts that we have here times 0.8, and its maximum use is going to be 96 watts. And the reason this one is 96 watts is because it has both the USB 3 QC3 and the 19 watt USB-C on there. So it's a bi-feed thing, so powering both of them at full strength. Most of your devices don't use that all the time. They're talking about the maximum continued usage, but it does give you an idea when you're buying an inverter of how big of an inverter are you looking for. So let's just say, for example, we go with a small inverter. And let's say it's 800 watts. Now, there are two ratings on an inverter. You have the continuous and you have the surge. What is the difference? When you turn on a device, specifically, usually devices with motors, anything that has a motor that needs to start up, it will have what they call a surge. And that means it takes more power to get started than it does to just continuously run. So for example, you may have let's say you have a small refrigerator. I have a little freezer. And my little freezer runs at 93 watts. Kind of a coincidence, it's very close to this here. It runs the whole freezer at 93 watts, but it has a surge of 930 watts, which is 10 times the constant consumption of this little freezer. And so this is true for most devices that you will find out there. Now, there are some that don't really have a surge. For example, if you don't have a motor in it and it's just basically a small heater and you're just gonna plug it in and all it's doing is heating up a coil, usually as soon as you turn it on, the power that it's pulling is gonna be pretty consistent. If you have motors that have to start turning, air conditioners, anything like that has those big motors in it, those are well pumps, anything like that, ceiling fans, anything that has a motor in it will need a surge capacity, especially if it has a compressor in it for refrigeration of any kind or air conditioning, anything like that. So keep that in mind, that you have to watch both of these numbers, and keep also in mind that inverters are notoriously exaggerating their numbers here. And this is why you'll see a lot of us YouTubers especially run tests on these things to determine. It says that it can do 800 watts continuous and 1600 watt surge. The question is, can it do it? And then the next question becomes is, well, if you had a device that ran at 795 watts and it could do 800 continuously, but you were going to have that device running all day long for, let's say it was a well pump and it was going to run for, 10 hours straight. Would you want it to run right there at the edge of its maximum capacity? Or what happens if the inverter deteriorates a little bit over? Would it stop working? So these are the type of things you need to take into consideration when you're buying an inverter. Is first of all, know that an inverter is bought to match the voltage of the battery. Very, very rarely will you find an inverter that works with multiple voltages. These two, usually you buy batteries, that's the end of it. If you're going to a 24 volt system, you can put two of these in series and create a 24 volt battery. Your charge controller, which is another device we'll talk about here in a minute, usually those work with multiple voltages. Your solar panels, usually those can work with multiple voltages, but your inverter is one of those devices that simply will not work with one of your things. So if you're looking for future enhancement here, you need to understand if you have this aspect of it right. And in order to know if you have this aspect, you need to know how much power you're going to need. And this is where performing some kind of audit on what you're doing becomes important. You're going to want to go through and figure out how much all of the little devices that you have are using, how much power they're using, so that you can actually understand when you get down to this list. So we have the little charger, and let's say we put in a computer and it runs at, let's say, 3 amps, and that would be my computer. And let's say we have a fridge and it runs like this one down here at 1 amp when it runs. Now, here's the question for you. The part that makes estimating this so difficult is that when you plug in a refrigerator, we all know a refrigerator comes on when you first plug it in, but when it gets cooled off, it stops using power. It shuts the compressor off, just like your air conditioner. When you first turn it on, your house is warm, it starts running and it produces cold air. But once it gets cold in the house, it turns off. Well, it stops using power when it turns off, or it stops using most of the power when it gets down to temperature. So understanding what a refrigerator would do based on saying I have a refrigerator plugged in all day isn't necessarily the same as saying what will a refrigerator use if it's plugged in all day. So I happen to know this freezer right here will run all day long at 93 watts, but it will only use 1.2 kilowatt hours. Now, what does that mean? So 1.2 kilowatt hours is a measurement of power over time. And so let's talk about that. And this is where things start getting complicated and people start tuning out. But if you can grasp the concept here early, it will make your life working with solar much easier. So a kilowatt hour is 1,000 watt hours, and a watt hour is a watt over the period of an hour. So let me give you an example. If I have a device that uses 1 watt, we already talked about this one uses 93 at full strength. But let's say that I had one of these to charge a phone, but charge it really slow, and it was going to use 1 watt. And I plugged this into my phone and I left it run for 1 hour, I would have 1 watt hour used. A kilowatt hour is that times 1,000. It's a 1K watt hour. So it's basically the same measurement, but just multiplied by 1,000. So that means that if I have a device that's using 1,000 watts and it runs for 1 hour, it would use 1 kilowatt hour or 1,000 watt hours. Being exactly the same, these are exactly the same. 1,000 watt hours is the same as 1 kilowatt hour. Now, The question you're asking is, why is this important? And let's get to that. When you look at a battery, it will tell you, for example, most 12-volt batteries these days will say this is a 12-volt battery that is 100 amp hours. And you're saying, well, up here we have watt hours, down here we have amp hours. Why is this useful? Well, it is, but you have to understand the technical behind it. An amp being pulled from a 12-volt battery is the voltage times 1, being 1 amp, and that means that a wall plug that puts out 120 volts at 1 amp is 120 watts. A battery that is charged up to, let's say, 13.6 volts, it's sitting at float, and when you go to pull 1 amp from that, you're going to get 13.6 watts at 1 amp. Now that means that if you need to run your charger that is 1 watt, then that means you need this 1 amp divided by 13.6, because you're only going to use part of that amp. You're going to use very little of that amp. So 13.6, wow, that's very small. 1 watt. You're going to use 0.07 amps equals 1 watt. So that means that this charger that runs at 1 watt, running off of this 12-volt battery, is 0.07 amps. Now, amp hours work the same way that watt hours work. It's a measurement of that power over the time of an hour. Now, you can slice and dice it as many ways as you want. You could change it every second and have to take all the 60 pieces of it from the 60 seconds and add them all together, and then take all those minutes and add them all together to come up with your watt hour. Or you can make some basic assumptions and say that if my fridge is running on 1 amp and it's using 1.2 kilowatt hours, and I know it's using 1.2 kilowatt hours, then how does that relate back to the 93? So let's figure out, what would 93 watts be for 120 amps? So how many amps would that be? So and this is where the math gets very confusing, and I'm going to double check my chat and make sure that if you have questions, please let me know. I'll be glad to answer them. So here we're going to take 93 watts and we're going to divide that by 120, meaning that this is 0.775 amps. Now, if I have 0.775 amps coming out of this 120 volts, the question becomes is, how many amps does it come out of this? And that's why this is measured in amp hours over here. This is a 100 amp hour 12 volt battery. This is a 120 volt wall plug. But all the math is interchangeable if you know how to do the calculations. So now we're going to take the same 93 watts and find out how much it takes from this battery. And we're going to assume this battery is sitting at 13.6 volts. So 93 amps, or 93 watts, divided by the voltage, which is 13.6, is 6.83 amps. Now, I have 100 amp hours here, and that means that if I ran this refrigerator at 6.83 amps non-stop, I can take 100 amp hours, this is for an hour, 100 amp hours, and divide it by 6.83 amps per hour to run that refrigerator, and I can run that refrigerator for 14.6 hours. Now, here's where things get interesting. You say, but Matt, you said this refrigerator only uses 1.2 kilowatt hours. And if we take this battery, knowing all the mathematical formulas that we just learned, and take 13.6 volts times 100 amp hours, we have 1360 watt hours or 1.36 kilowatt hours. So that would mean that this battery has enough power to run this refrigerator for 14 hours, but yet we show the math that the known fact is that this refrigerator can run for well over 24 hours because it shuts off and on and off and on and off and on. And that off and on is what allows this 14 hours to become twice this. Let's say that it runs only half the time. Let's say it runs for 5 minutes and then shuts off and sits for 5 minutes. And then as it gets warm, it runs for 5 more minutes and then shuts off for 5 more minutes. And that's where this mathematical formula becomes complicated, because knowing what this fridge uses over a period of a day is 1.2 kilowatts, and what it says it's going to use here, which is 1.36 for a 24-hour period. Knowing that you only have 1.36 available for this to use all day is where things get very complicated, and you're only going to be able to run it for 14 hours, which means this is going to be using a whole lot more than 1.2. It's using well over 1.36 for 14 hours. So the question becomes, how do you know these things? And the easiest way is to buy a little measurement tool called Kilowatt, and that is spelled K-I-L-L-A-watt. This little device allows you to plug into a 120 volt outlet, plug in another device to it, and it'll measure the amount of electricity that's used for this here. I happen to know this number because it's in my coffee trailer, and I know exactly how much battery power is missing when I only use the thing. Now, there are some other elements that you need to consider. This is a great example of how to start the system. But you also need to take into effect that when you start building a system like this, I'm going to remove all this from here. When you start building a system like this, there are going to be losses. Every time you convert power, there are some losses. And what I mean by that is that if I convert my power from DC to AC, like we did here with this inverter, because we connect this inverter like this, now we can plug the refrigerator in and we can measure how much it's using. We also have inside this battery, usually you have a BMS that will tell you how much voltage is gone, and you could use the kilowatt here to determine the difference between what the battery says was used, what the kilowatt says was used, and the difference is, let's say that this says that 1.4 kilowatts was used, and this says that 1.2 kilowatts was used. You know that 0.2 kilowatts was used by this inverter to convert the power from one type of power to one type of electricity to another. And these are the losses you have to take into account when you start doing these type of conversions. But that all said, the two basic parts that you need to understand to get started is that you're going to have to take, if you want to run standard wall plugs, you're going to have to have an inverter. This inverter will take your DC power and convert it to AC power. It inverts the power coming in from DC to AC and allows your plug-in devices to use. These are the two basic first components on practically any solar system, and knowing this tells you how big of a battery you need and how much power you need to do. And those should almost always be the first two items that you're going to really need to know How much power do you need? And then what kind of battery do you need to supply that power, and how much that power is going to be? Okay. The third component that we're looking at here I don't know if that's the third component here is going to be the charge controller. And the first question usually you get from a charge controller is, and there's a couple of very important aspects to a charge controller. The first one is well, what does it do? And the simple answer is the charge controller controls charging your battery, and it takes the power from your solar panels and converts it to what matches your battery using the charge profiles that we talked about before. So this is where that intelligence is. Let's draw the solar panels on here because it's the fourth element. We're going to draw the solar panels on here. We're going to have 4 solar panels, and we're going to feed them into the charge controller. I did not put wires on the panels yet because we'll talk about that, and we talked about it a little bit earlier, but we're going to talk about it a little bit more in a minute. But the charge controller, the first thing it does is it will take the power, and this is the difference between a PWM charge controller versus MPPT. Now, I am going to talk about an MPPT charge controller today because there are very, very few cases where a PWM is useful. And one of those cases is if you have a 12-volt system and you have a charger that is basically charging at 15, 16 volts, like one of the little eco-worthy ones to keep your boat battery charged or something like that. You can go straight to the battery and the trickle charge is so small, and they even have some solar panels that work like that. The problem is now with the way the batteries work, the BMS takes care of that, and you need a little bit smarter thing, especially if you're going to have more than a single panel or have any type of system that's going to have any significant amount of power. You won't want to mess with the PWM. You'll want to stick with the MPPT. Let me explain why. Earlier, we said that we were going to run those panels in 2 in series and then parallel from there. So we ran it like this. We had these 2 in series, and these were 30 volts apiece. And they were feeding in at 60 volts each. And they were 10 amps apiece, so 60 volts at 10 amps here, and 60 volts at 10 amps here. And so that meant that it fed in to the charge controller at 60 volts at 20 amps. Because up here when we put them in serial, the voltage doubled. And here when we put them in parallel, the amperage adds up. So here the voltage adds up, and here the amps add up. And so now we end up with 30 and 30 is 60. So both of them are feeding down 60, and 10 and 10 is 20. So that means that these 4 panels, and going back to the same math we used up here, 60 times 20 is 1200 watts. And that math, once you learn that math, you can use that throughout the entire system. That is basically what they call Ohm's law, which is volts times amps equals watts. But that also means that any way you can move that formula around, any of you from your algebra class that want to change this around from amps times amps divided by, what is it, amps divided by watts equals volts, whatever you want to do, they all work. And that's exactly the formula that you really need to learn The easiest way to remember it is volts times amps equals watts, the end, however you want to work it. So here, this charge controller is taking in 1200 watts. It's 60 volts and 20 amps. But we know that the 12-volt battery needs this to be at a charge voltage of 14.2 volts. So what this charge controller does is it has this profile sitting in it. And if you look at, and I can show you a Victron charge controller. Let me just flip this screen here real quick. I need to go, there it is. Actually, I want the Victron Connect app. I'm going to use the Victron Connect app here. So we're going to take my system here. And we're going to look at the charge controller. All right, and then we're going to look at the battery. And I'm going to click on expert mode. And we're going to see here that I've got a absorption, which is the same as bulk charge at 56.2. And I've got my float voltage at 54. So this means that every charge controller, or most of your good charge controllers, a lot of the cheap Chinese ones will have this same information, but they'll be built in. And you'll buy the charge controller and it'll say it charges at this rate. And it doesn't really have a float or an absorption time, or it goes from basically bulk charge, it's stuck in absorption forever, meaning that it got all the way charged and now it's just going to sit there at the top just saying, hey, are you full, are you full, are you full? And so that's where this comes in very handy for some of your smarter charge controllers. They have the second level, which is that float voltage that you see here. And this allows you to configure all of the stuff that we talked about up there. But this is why I like the Victron devices, because they allow this. Now, many of your BMSs allow the brains of this to be monitored and watched, because your BMS is your battery management system. It is there to watch what's going on with a charge controller, to watch what's happening, and to protect your battery. It is not designed to be the first line of defense. It's designed to be the last line of the defense. To keep you from overcharging your battery, to keep you from breaking a cell because you put too much in there, to keep you from doing things that you shouldn't be doing, and to shut them off, and to give you that overvolt protection. To shut them off early so you don't kill your battery and drain it down too far. Because a lot of your lithium iron phosphate batteries will shut down at 10 volts or so and consider that zero state of charge, but that prevents those cells from being damaged, and that's why you can go from zero charge every day up to 100 and back down to 0 and up to 100, because they protect it with that BMS and allow that charge flow to be in the middle. Okay, so that said, once you get to this point, the charge controller has to take those numbers and convert them. So what would end up happening is that this charge controller is going to, and we're going to do the math here so that you understand how it works. It's going to take 60 volts at 20 amps, and it's going to convert this 1200 watts to 14.2 volt charge rate. And let's say that we have, it's coming in at full strength, everything is all here, we have all 1200 watts. Now, most likely you're not going to get 1200 watts all the time. You're going to have some percentage of that. But for argument's sake, we're going to do the whole thing so that we understand the maximum amount of amperage that this is going to push down into that battery. So at this point, we are going to take the 1200 watts, and this is where reversing this formula becomes useful. And we are going to divide it, instead of dividing it by 60 to get the 20, we're going to divide it by the 14.2. And when it converts this, 1200 divided by 14.2, it is going to output to the battery 14.2 volts, and it's going to do 84.5 amps. Now that means that this charge controller, to be able to handle this input, would need to be able to handle 84 amps into a 12-volt battery. Now this is where people say, okay, well, an 84 amp charge controller is very expensive. How can I buy a less expensive charge controller? Well, the simple way to get these amps down is to make this battery bigger. Because if you remember, we took 1200 and we divided it by 14.2 to come up with the 84 amps. Well, if the battery was twice the size, it would be 1200 divided by 28.4, and it would be 42.25 amps. It would be half the amperage. And if it was a 48 volt battery, it would be 21 amps. So as you can see, the reason that people change to higher voltage batteries is because it allows, first of all, it's much cheaper on your charge controller, but it also allows this amperage to be much lower and the wire size that you need becomes smaller. And people say, well, okay, so if I want this, what kind of wire is going to cost for 84 amps as opposed to a 48 volt system where I have 21 amps? It's huge difference in cost. And that's where the cost of this, once you start doing the math on this, you need to match that to the size system that you need. And for example, my solar shed has 6,000 watt inverter. So if you take a 6,000 watt inverter and divide that by the 14.2 volts that a 12 volt system would have, in order to actually feed this system, we would need 422 amps. Well, 422 amps would require two 4-aught wires, which are about $12 a foot in order to run this, because those are 300 amps a piece, and you're gonna need two of them to make that happen. So this is why in a 48 volt system, it would be a quarter of this, which means it would be 106, actually rounded to 105.5 or something like that. So 105.5 amps for 48 volts. And so this is why it is important that you understand the battery size that you need and the inverter that you need and the charge controller. 9 times out of 10, most of these, if they're Victron, most of them will work and you can use them when you can upgrade. So if you go from a 12 volt system to a 24 volt system, you can use the same charge controller. If you take one 12 volt battery and series it with two batteries, you can reuse the batteries. If you go from, but the inverter is one of those where when you buy it for that battery voltage and that's the end of it. So this is the basic system that you're going to need if you're going to set up a solar system. Now, my suggestion is if it's your first solar system, you do a very small 12 volt system. You could even go with one panel like this. You have one panel, feed a small charge controller, feed your 12 volt battery on this side of the equation, and then on this side of the equation, you have an inverter. Take this 12 volt power and convert it to AC power so that you can run your devices. Now, hopefully, this kind of gives you an idea of an outline of a solar system, a basic solar system. Now, what I would like to do is to take this and build this into a chart that we can offer going forward for others that are starting this wow, that chat is not the same chat. Oh, yes, it is. Just noticed the music? I don't know why my chat died. I can see it, but I can't. I'm going to try to fix it real quick, guys. Give me just a second here. I'm just going to try to close this. And put that there. And change YouTube comments. I think I also need to take this. Almost there. I don't know why this went crazy. It kind of does these things from time to time. Okay. And that should fix it. Now let's go back here. And turn this off. There we go. Okay. All right. Hi, CJ. Good to see you. Hope everybody's doing well. Anyway, that's the basics of a basic solar system. That is how it works. What I want to do is I want to take this what we drew up here on the board. I'm going to convert this into a document. I will have it available on future live streams and future videos where you can sign up for an email list and get a copy of it free. I think I will do a diagram that outlines the different system here. But the only other thing left really for us to discuss tonight is what we call the AWG or America Wiring Guide chart. I think it's important that you understand this because if you catch on to the formula here that's used to calculate how many amps are needed to run particular devices, whether that be a wall socket or whether that be the battery in your 12 volt or your 24 volt or even a 48 volt system, you're going to want to understand what kind of wire and how big of a wire you should use. It becomes very easy for someone like me who deals with it every day to say, oh, well, that's 385 amps. You're going to need, 4/0 is this size wire, and so you're going to need 2 of them, or you're going to need this, you're going to need that. But it is much more difficult when you get started because everything that you do, you have to put some thought into it. So let me show you some shortcuts that you can use to and I want to find it in the code book, what chapter it's in. And I have the code book here. It's chapter 310-16. So let me see if I can do the NEC chapter 310-16. It's perfect. Let me just show you this. So this is, let me just make sure that that's actually working. Yes, it is. Okay. All right, so this chart is produced in the code book, the NEC code book, and this one, I think it's the same one that I have here, is 14. Looks like it's the same one that I have here. So this is from the 2023 code book. At least I hope it is. And some of the text looks like it might be different across the top there. So maybe it isn't from this year, but it could be though. It looks like it's all the same though. So even if it's not, it is the same. But this is a very important chart for you to understand how to use. So you'll see down the left-hand side, we have AWG. You'll also see that there are some CK mills listed on here. And the sizes that are used around the world are measured in millimeters, and the sizes we use here in the States is usually the AWG, and that's because it comes from this code book here. And this code book is basically a list of all the different requirements for connecting things and setting stuff up. And it has a lot of really pain in the butt stuff that you have to deal with when you're dealing with getting inspections, but it also has a lot of stuff that's really important for safety to make sure that you don't catch yourself on fire, burn your RV down, your house down, or even worse, hurt or kill somebody. So this is one of those items that's in that book that talks about wire sizes. And this is one of those that we talked about a few minutes ago when we looked at 300 amps, what size wire was needed. And if you look at this, you'll even see that my assumption of 300 amps for 4/0. So let me show you how to read this. Down the left-hand side, you'll notice that there is an AWG, size AWG listing. These are all the common wire sizes that you will find in your Home Depots when you're ordering wire off of Amazon or from marine places or whatever. And there's different types of wire for the same size. So you have to be very careful when you're ordering wire. When I first started, one of the biggest mistakes that I did is I ordered some wire without paying attention to what I was doing. And the first one I ordered was copper clad wire. When I got it in, it was basically aluminum wire that had a copper clad wrapping around it. But it didn't support, it had the resistance to some of the chemical resistance, but it didn't actually support the amperage that I needed. So I ended up buying a second set of wire. I think that was and the second set I bought, I don't even remember what the difference was. Well, on the first set, I bought the wrong size wire. On the second set, I bought the copper clad wire. So it took me 3 tries to get the right wire. And the thing is it's not one of those things you can live with. And it might have been okay if it had been just, a temporary little system that I was using for demonstrations or something like that. But this one was in my RV that I was sleeping in at night, and it was powering me off grid 24/7. The last thing I wanted to do was wake up with a fire in an RV and kill myself, my wife, my kid, my dogs, whatever the case may be. So I encourage you to take very serious note to this one here. And let me go over some of the common ones that you probably have always wondered where that came from and why is it that way. And this one really answers that chart. So let's look at the first column on the left-hand side. Talks about 18 gauge, 16 AUG and gauge usually run hand in hand. People use those words interchangeably. You'll hear me say AUG, where it's AWG, which stands for American Wire Guide, which is a company independent company that forms these guidelines, and the NEC code book does not set the guidelines. They set the guidelines to be used. They don't necessarily make the actual chart or the guidelines for the AWG. So here you'll notice that there are some that are very, very common that you see in your house all the time, or in your home all the time, or in very common locations and you don't know about it. So for example, a standard household wall outlet that has 2 vertical slots like this on this thing here and a ground at the bottom. If they're both vertical, this is a 15 amp wall socket. And you'll notice here that for 15 amps under the first column here under types TW or UF, meaning the standard wall type, standard wall, let me explain the difference here. Romex kind of wire that's in your walls that's not individual stranded wire that's in electrical conduit or something like that. The Romex wire for 14 gauge supports 15 amps, meaning those wall outlets are probably ran with 14 gauge wire, and that's why those wall outlets are limited to 15 amps, because not only is the plug itself rated to support 15 amps, but the wire is rated. And that way, if you plug something in that pulls more than 15 amps, instead of that wire melting and shorting and causing a fire in your wall, it would pop the breaker, and the breaker would stop the wire from melting and causing any damage or causing your home to burn down or whatnot. That does not mean that you can't do something stupid and still have that type of problem. It doesn't mean that you can't hook up a device that uses 8 amps of power and it shorts out and it causes all kinds of fires and stuff like that. Christmas tree lights come to mind, or at least the older ones that used to pull lots of power before LEDs. But they're still dangerous to a certain extent because most of them still have some variation of 120 volts running through them. A lot of them now are running off of 5-volt systems where they have little converters in there. They step down the voltage, making them extremely safe compared to what they were. The second one on this chart that's really important you should take note of is the 12 gauge wire. You'll notice it's 20 amps. And that is the 20 amp wall plugs that you'll see that have the one vertical and one horizontal on the left-hand side. When you're looking at it, it's on the left-hand side. And those allow wall plugs to pull 20 amps. And that means that it has either that TW wire, which is the Romex wire, that is 12 gauge, or a larger wire in there. Now you get into some of the other wires here. Let's talk about the 10 gauge wire or the 10 AUG wire. And these are usually like your dryer plug. A lot of dryers in your home are 30 amp plugs. And that means that you probably have that TW wire or that Romex wire of 30 amps. And then you get into 8 AUG, which is the 40 amp wire. If you get into 6 AUG, it's 55 amps, and so on and so forth. And this starts getting into the others. Now, the one thing that's very important to notice about this chart is AC, DC, and voltage makes no difference when you're looking at these wires. Most of these wires are all rated for 600 volts or less. And so you need to pay very close attention to that. When you look at a piece of Romex, it'll say 600 volts or less. That is what is standard for being able to be used in a home or something like that. And that's why they're rated that way. Once you go over that, you get into a commercial grade type of wire, and all the rules change, and this chart doesn't even apply. There's a whole new chart that applies to it. So you want to pay close attention to that also. So you're limited to 600 volts, and that's AC or DC for a normal solar system or running your house lights or anything like that, which in most people's case, a 240 volt outlet or a 110 outlet, you're not going to be running anything that's that high voltage because of the significant danger that's involved with it once it starts getting into that high voltage. Now, let's look at the other columns here, and you'll notice there's some important aspects to this. The first column that we were talking about, which was Romex, you'll notice at the top it says it can handle up to 60 degrees Celsius or 140 degrees Fahrenheit. That means that it has a rating of how hot it can get before it starts to deteriorate and possibly melt and start shorting and stuff like that. So you'll want to pay close attention to that if you're going to run this close to the edge, you might be better off going with a little bit better wire. Quite frequently, if I have something that's running on 15 amps, but I know I'm going to be running it right at 15 amps all the time, I'll go ahead and use a little bit bigger wire. I'll use the 12 gauge in order to have that safety barrier in there. Now, the standard code book will tell you that you need to build in a 20% buffer anyway. And that means if you are running something that is, and you'll notice that most wall extension plugs are 12 amps or 10 amps. Most extension cords are 10 amps or 12 amps. And the reason being is that they only support 10 amps because the plug supports 15. The 15 supports enough amperage for that. And so everything has that buffer built into it. So that's something that you're going to want to pay attention to. Now, I do need to tell you at this point, I am not an electrician. If you are uncomfortable with that, I'm telling you how I use this, how I interpret it, and what I use this for. If you need an electrician, I encourage you to hire one. They are great at understanding this. Most of them have gone to school, done hundreds of hours to learn all the contents behind this huge book of 800-900 pages of code and things like that. I use it explicitly for solar, basic electrical wiring and stuff like that, and don't have anywhere near the education of an electrician. So please, if you're uncomfortable doing it yourself, hire someone to help you out, and don't do it, and be very, very careful. That said, you can do this yourself, and you can do it safely as long as you're very careful and cautious and understand the dangers of what you're doing, and pay very close attention to some of the items that are important. And I suggest that this is one of them, the size of the wire. So for example, when we were talking about your 12-volt system having a pull for an 800 watt inverter. So the 800 watt inverter at the 13 volts, if I remember correctly, and we'll do the math again here just to make sure we understand it, 800 watt inverter at 13.6 is 58 amps. And so that means in order to get 58 amps plus 20%, you would need to take the 58 times 1.2, and that brings you to 71 amps rounded up. And that means that you will need 3 AUG wire to support that if you are using Romex. Now, there are multiple types of temperatures and wires here. You'll notice if you go over one column, you have THHW, which is probably the most common name there, which means this is the individual wire that's usually wrapped for water instances. They're burial type things where you're going to bury it in your yard and run a pedestal out to an extended plug or something like that. That's what THHW stands for, wet related items. There's also THHN, which is in the next column over from that. And there's a bunch of other names for it and different variations of it and stuff. And this is why it's really important that you understand the wire that you're buying. Don't just look at the gauge and just assume that it's right. This can save you a lot of time and money of redoing things. THHN, which is the third column, the temperature rating goes up considerably. If you'll notice, it will handle up to 194 degrees Fahrenheit. Now, I have done a ton of solar systems, and I have seen 180 degrees quite commonly when I'm testing things. So if you're looking for something that's going to support good hot temperature, then it's probably good for that. Now, most of these are based on your home using 120 volts or using that. You're probably not going to find them for your larger wires that we have down there. Now, some of them, for example, your inverter wires and stuff like that, if you need a 6 gauge or 4 gauge or something like that, then you can find them. A lot of them, what I do is I order marine grade wire, which is rated at 205 degrees Celsius or 105 degrees Celsius, which is off the edge of this chart. And you will need to look at the different sizes of those wires and the specs behind those wires to understand how much amperage they can support. So for example, on the marine grade wire that I was talking about when I said it can support 300 amps, it is, you'll notice here, there is no 4-aught wire that supports the 300 amps. You would need to buy that type of wire to get it to work, and nothing in this chart would actually do that. None of the types that they have listed. So you need to pay very close attention to the wire you're buying. Make sure that it fits the application that you're using. For example, THHN needs to be mounted in a metal conduit of some kind, either one of those metal tubes or in a box or something else like that. Whereas Romex is made to be placed inside your sheetrock walls, inside your home, and it's not supposed to be in conduit. And and a lot of people say, well, how does that matter for the wire can support it if the wire can support it? A lot of the heat dissipation is based on how the wire is placed. In other words, if you place a wire in an open wall or up in an attic, and the air can get to it and it can breathe, it can dissipate heat a lot easier than if you crammed it into a tube with 2 or 3 other ones and it didn't have any way for that heat to escape. So that is why it's important that you understand that. This is one of those charts that if nothing else, I would suggest that you refer back to it. You can find it just by doing a simple search for NEC code table 310-15, I think is what it's 310-16 in my book. So this must be probably the 2023 version, or the 20, it doesn't say, but my 2023 version of the book is table 316. But you can look it up. It's quite commonly available. You can find it anywhere on the internet. You don't have to buy a code book to get one to see this chart. But I would encourage that you do take that seriously and work with that one. I'm hoping. I'm looking for screen. There it is. All right, so I'm hoping that is got everybody where you need to be tonight. I'm going to end it here, and I will follow this up with building a chart and a free download for everyone who wants to sign up for the email address to get, and that will follow this this video. I will attach the link down below, so if you're interested in that, and you're watching this in post-production, post-live, or after I've recorded it, just feel free to follow that link down below and you'll get a copy of it in your email box right away, just for signing up for the email list, and I'll keep you informed of things coming out. It's been a great week for everybody. Thank you for coming. I'm extremely excited about the plans I've got for the solar shed coming up and all the different solar systems. And I am going to take the next 2 months and go back to the basics of solar systems. I am going to cover practically every conceivable basics concept there is, from basic solar system as we did tonight, to understanding batteries, to understanding charge controllers, to understanding, I've got a list of probably 50 different items, and I want to come out with a very extensive library of those items for you guys to use and reference when you have questions and you run into things. As I said before, thanks for watching. I do want to celebrate a little bit tonight on the subscriber base. You guys are incredibly good to me. I know that as of tonight, I have 800, where is it? I have 18,875 subscribers. Thank you so much again for being a subscriber, for watching my channel, for liking my videos, for coming back week after week and listening to me jabber. I've been spending a lot of time out in the solar shed working, and I'm hoping that I'm bringing you the content that you're looking for. If not, I want to hear about it. What do you want to see? I'll be glad to make that video. I'm going to refocus my efforts on making sure that each and every one of you know how to build the solar system that you need and what are the basic concepts that we're missing. I continue to advance myself into bigger and bigger systems and forgetting that where I come from is where I started. There was not a lot of information around how to get started, and that's where I really want to focus my efforts. So if that's you and you're looking forward to taking that trek with me, I look forward to you subscribing, and we'll see you on the next one. Thanks for coming. Thank you for watching, and thank you so much for being a subscriber. I appreciate it. You guys have a great week. We will see you next week.